Good evening, y'all. Let's see if that mic is on. Hey, it is! Hey! That works out very well. Yeah, we're back to the regular Sunday night, 7 p.m. after a couple weeks of just shenanigans and whatever. I felt like, hey, Brooklyn, good to see you. Yeah, gotta do some more work on DMX powered winches. And I gotta start off with, I made a whoopsie doodle. I'll show you what it is. You'll probably spot it before I do. So this is the new drive barrel design that we were working on, I think a couple of weeks ago now, or whatever that was. Remember, this is the part that fits through the ratchet holder mechanism. Obviously, there's a bearing that goes in there, and then this supports the ratchets in the middle, the tension plate on the outside, and then it interfaces. This is the part we were working on. We were working on this interface to the actual shaft. So this is a piece of 3/16 stainless steel, platinum steel, plated steel? I don't know. PLT steel from Menards. That cost me, that doesn't say, very little, like $2. With a couple of grub screws that'll go in the outside there, although currently I've just put the heat set inserts in. So this is an okay design. It was kind of a pain because when we designed it, I can't even get it out now. The theory was, right, the profile of that hole is sort of flattened. It's like a double D-shaped hole. I don't know what you would exactly call that. But if we look at the design over in the model, I think it'll make more sense. Yeah, so that's the shape of that hole, right? So the idea is we flatten off two opposite sides of that shaft, and that gives us some purchase for the grub screws that go in the sides to actually like grab onto something and secure that shaft in place. With the shaft as it is, actually, it's a really tight fit to that hole. So like the grub screws, I mean, I'm gonna put them in, but like not super worried about like slipping. I am a little worried like about just the general forces on this 3D printed shaft, transmitting all the force of the stepper motor that will be on this side to the shaft itself. But we'll just see. Maybe we have to change materials or change perimeters or something like that. We'll cross that bridge when we come to it. That's not the dumb thing. The dumb thing is this, and some of you may have spotted this before I did, right? So this normally sits in here, right? And the ratchet goes around the outside, and the friction wheel and the gaskets go here. And remember the bearing, our 608 skateboard bearing, goes in that hole. But I did it bad. You can't actually get the bearing. Like, look at this part. Like, the bearing is supposed to go there. Focus there, camera. There we go. Supposed to go there in between those two notches. And I haven't left any way for the bearing to actually get there. I figured that out about 20 minutes ago. I was like, well, that's just great. So we might take a whack at coming up with some more clever design to fix that later tonight. I mean, maybe we try and make like the profile of this attachment smaller than the interior hole on that bearing. Maybe. Seems like a little bit of a stretch. So anyway, maybe more clever things to come in that area. But I think I hear, yeah, so actually as you were watching beforehand, I had a 3D print going just before things started. I should reach over and grab the build plate there. Just some real quick and dirty spacers to go between the shaft and the 608 bearing, which are hopefully the right size. And if not, it was an 8-minute print to do 4 of them. So if I've gotten it wrong, we'll spin up another version real quick and get those running off. And so this is the part I think I don't remember what week anything happens anymore, both on this stream or like in actual life. So like I don't know when we did this, but we are working on, where's the table? There's the table. Working on like this support, which will hang off of our piece of truss and sort of support this shaft in the middle of its run. So, might be finally time to take this price tag off. Let's do that real quick. Wow! Oh, I've spilled my beer. Oh dear. I've spilled the beer. Here, you can... I've spilled the beer all over the thing. It's fizzing up. It's a really... I guess this is a good chance to say. It's a very tasty beer. This is an amplifier by Two Brothers Brewing Company. But right now, it's being very tasty and also all over my workbench. But that's what rags are for. I feel a little bad that Cookie's not here to see this. You know, it's not fire, but like it is the kind of like wanton destruction that I feel like is very much in their wheelhouse. Let's just get that a little bit mopped up for now. So yes, amplifier, a tasty beer from Two Brothers, and also like not a great workbench cleaner. So if you were looking to use beer to clean your workbench, maybe amplifier is not for you. All right. We'll just move, maybe we move that off to the side there for a little bit. Bergwood has a roll of gaff as a cup holder. It's not a bad idea. I have gaff just hanging out. I don't know if you can see it on this camera. My tape storage is just up there next to the 3D printer. It's not a bad idea. It's what we used to do on tech tables for in theater. But the workbench is a little bit space limited these days. Ooh, this might be too tight of a fit. Well, maybe not. Where is that camera? Oh, I moved the camera over to show you the beer. Let's come back to the 3D printing. See the little bits of beer littering the bench now. All right, let's grab some pliers and see if we can't get this down into a... So I stole the interior dimension for this off of another part. That was a really snug fit. And as promised, this is a really snug fit. So now let's see. You know what I probably should do is I'll get the bearing flush to it while it's on the end, and we can kind of get at the whole assembly here. And then we'll slide it down. So I'm just going to kind of use the workbench here to press everything together. And we'll use the pliers to hopefully get everything all nice and in there. Let's see here. A little bit snug, but that's okay. We don't mind there being a snug fit between the spacer and the bearing, because the whole point of the bearing is that it bears. It helps things run smoothly even when there's a really tight friction fit. So there's our bearing along with our spacer. So now I'm going to just take the pliers, and if I can do this without stabbing myself, just going to slide them down the shaft a bit. And then, here, I'll take this spacer that I prepared earlier. I'll pop the spacer out of that, or the bearing rather, and we'll see. Yeah, so there's our shaft bearing with our 608 skateboard shaft in it. And we'll see, so like when we were messing around with the sort of drive barrel, we had to put two sort of retaining pins on it to prevent like any lateral motion from causing it to slip out of the bearing. I didn't include that in this current spacer, although it wouldn't be terribly hard to add. I'm not sure if it'll be necessary. That's a really tight friction fit in there. But that's something that's gone right today. That's very exciting. Maybe I'll grab a second one of those and just plop the shaft in, just because that'll be kind of actually a nice way to do some work holding while we're working with the shaft tonight. So there's another holder. Here's a couple more pins, and we have a spare bearing here already. So we'll slide this whole thing down, and we will assemble another one of these. Just kind of just use the workbench to kind of press everything together. I know you're just looking at the top one. The shaft is pointing straight up at the camera. Ugh. Let's see. Wonder if do I have channel locks? Yeah. So I think what I might try, because it's being a real bummer to try and get the bearing down over the spacer itself, is just to use a pair of channel locks on the shaft itself, just so they won't go anywhere, and use that as a surface to press against as we try and get everything to come together. Oh, yeah. It's a little tight. Oh, get in there. Oh, get in there. Okay. So there's our second bearing in there. We'll get our, I don't know if this one's going to need any filing. We'll do our second. Oh, no, that's a pretty good fit. Second filing there. And then we would get a couple of pins. And I realized after we printed these last time, so one thing I had done to create the holes for these hanging pins in some of the original models, right? We sort of ripped this design off of another model and then sort of modified it further for this model. I realized that original one, I had actually sort of, we basically took this model and used that to cut a hole out of this model. And when I had done that originally in this other part that we were working with as part of the Kabuki drop, I had actually upscaled the 3D model of this pin by about 3% before using it as a cutting tool, just to provide like a little bit of extra clearance and a better fit, like just, for precision's sake. And I didn't do that with these. I just took a straight cutting of the parts. So they do lock together, but it's a really snug fit. But they can be sort of coerced into position. So if I do, and a little bit of filing on that top lip goes a long way, I have discovered. This one is not going to want to play as nice. Of course, there we go. A little bit more. Yeah, that first one actually isn't in all the way yet either. Let's see if a little bit more mechanical convincing will get that into place. Doesn't seem like it. Seems like something, maybe I have some spoilage down in there. But in any case, what we'll want for this evening is just for that to be like, that'll be a nice thing that'll hold our shaft in place while we're working on it. And, now it's a little hard to see that it's spinning. We'll put a little of our old friend blue tape on it. I'd kind of been leaving that price tag hanging off the end because it made it really easy to see if the thing was spinning. But there we go. So now when it spins, we'll see the blue tape move. And they're like these skateboard bearings, like they are exactly that. They're bearings for skateboards, so it's not like they're super low friction. In fact, they're kind of viscous. But we don't need them to be super low friction. We're going to have, I think, plenty of power coming out of our stepper motor to handle whatever we need to do. So, well, one minor sad already before pre-stream this evening, one decent success already. What I thought I would bang out, I've got an easy thing and a hard thing that I want to think about tonight. The easy thing I think is, so the idea is that this piece of metal is the shaft that's going to be the lift line that lives up near the truss that like lifts other lines that are suspending some other truss or batten or whatever down at, over the stage. So this is going to need some way of having a line wound up on it, probably in several places. So I think we're going to build a simple little barrel contraption. I use the word barrel for like far too many things. Drum, I think maybe is what we should call it. A drum that a line can be wound up on that has maybe a grub screw that can sort of be captive and keep it in one place. That seems like a fairly easy design. And the other one is we got to do some thinking about how we're going to establish like limits of travel for this thing, and we got to think a little bit about DMX control along with that. And there's a few different ways that I can think of that we might approach such a thing. So I'm not 100% sure which way we'll go, but let's bang out the easy project first, because to be honest, like discovering that spacing issue was kind of a bummer. And by the spacing issue, I mean like the fact that I can't put this into service as is because focus camera. Can't put this into service as is because the bearing doesn't fit over that. Like that's just such a silly mistake that I'd like to chalk up another win to get my brain back in gear before we go too crazy. So let's call this winding drum, and I'm just going to start with the model from that spacer because I know this interior dimension is just about right. And let's make our exterior dimension. There's no reason for it to be quite that small. Let's make it 1/2 inch or so. And I'm going to enlarge this inner dimension by 5/100ths of a millimeter, which seems a little silly, but at the scales that we're working, I think that will actually be helpful in actually getting the barrel in place. We also don't really need it to be this stubby of a thing. Let's make, how big should each of these winding drums be? Now we could do some math, but I feel like an inch of windable space is maybe just a little generous. So let's say it's 20 millimeters. So let's say this is the area around which our line will be rung. And let us make a nice little contoured end to sort of keep the line in place. And we can do that, I think, just with a couple of sketches here. So we'll project our whole body in, and we'll draw the profile of our drum, sort of drum ends, if you will. I don't want them to come straight up like that, though. I think I want them to have like a little bit of a curve. So let's do a spline, which is overkill but fun. So something like that. And then we'll have a little bit of a flat lip. We'll come down to our midline. So of course I'm gonna revolve this around a center axis, and that's gonna create our shape, and then we'll mirror it across to make our whole shape. And let's dimension that a little bit better. Let's not get too casual. So let's see, from center line, I guess I want the whole thing to be maybe about an inch. So this should be 25.4 millimeters divided by 2. Yeah, and that's, of course, our spline is going to be a little bit grumpy there, but that's okay. And I'd like this to blend nicely into the barrel, and I can do that by making this tangent line here horizontal. And that'll make sure that curve blends in nicely. Yeah, that seems right. Okay, so now we'll do a revolve of this profile around the center axis here, boop, to create our end cap, and I will just make that as a new body, and then I will just mirror that body across the center plane. Oops, objects should be the whole body. The object first, this one, mirror plane is this one, do a new body, and then we'll just join everything back together. Combine 1, 2, 3 things and combine. Okay, so there is our, oops, now what's happened here? Oh, you know what? I need to remember to include that center hole. I've capped off my center hole here. So really, this should come not all the way down to the center there, but let's leave space for our center hole. Do that, and then we will make sure we can only make that a construction line to make this a little bit easier. We'll revolve that shape, and now our center hole is back, so that's good. Okay, so there's our winding barrel shape, and now we just need a little bit of room to put our set screw in, so that we can actually affix this to some point on the shaft. So let's steal some geometry from an earlier project, which is one of my favorite things to do, and measure the depth and diameter of this hole. So this hole is about 6 millimeters deep, and its diameter about 3.2 millimeters. So what I think we will want to do, let's just make a sketch on that center plane, and I want us to go right down the center of this thing. Probably we'll make a 3.2 millimeter hole, and then we will extrude it just into the center. Object, distance, to object, turn that body off, object, 0 distance. Oh, I see. No, I have to actually, if that's the plane that we're drawing on, I want to cut this out of this body. That's what I'd like to do. Okay, there we go. So now I have a hole to put a grub screw in, and we'll have to do a little bit of grinding up the shaft to give ourselves a spot to attach that, but I think that'll be fine. Let's get one of those printing, and we'll see how we do. We'll save as an STL. We'll call this our drum. We will bring it into Prusa Slicer. I'm gonna throw away a few of my really stout settings here. Discard and import, and we want our drum. And let's check the orientation. That looks good. We'll just do a draft settings print for now because we're really just testing for fit. 32 minutes. I love it. So this is drum draft. Very good. All right, well, let's get the printer heating up, and we will get the... Now, oh, it's a good thing. I was gonna say, I think clipping a little here is what I think, but I think I was like, I don't have a paper towel anymore because I use my paper towel that I usually use for cleaning off the print bed with isopropyl to mop up beer off the workbench. But, you know, just little things. All right, let's get that clean. That's preheating. And let's get this loaded onto our flash drive. Get there. All right, and we will pull our G-code file. Now, I guess what I could have done is done a an adaptive print, right, with those curves on that barrel. We could have done this in adaptive, and that would give us slightly nicer curves, but really I'm more thinking about like is this the right sort of scale and size for this thing, and are the dimensions of the interior correct? So like we can do a nice adaptive slice when we have once we check those things. Right now I think it'll be just more better to get this thing printed and going. So pop that back in ye olde printo. And oh, there's still a spacer on the bed. That's funny. Well, we'll get one more spacer out of this. That'll be fine. All right. So that was the how long did that take us? 10 minutes? Fine. Actually, an actual short process for a change, which is rather delightful. So next thing I think we're going to try is thinking about how we're handling limits of the travel of our DMX winch, starting to think a little bit about how we're going to be actually controlling it with DMX. So the Wahlberg winches, which are sort of the closest commercial equivalent to what we're building here in microscale. And let me see if I can actually pull up an example of what I'm saying. When I say Wahlberg winch, just a brand. Wahlberg winch. Yeah, I think we looked at these a couple weeks ago, but they make like a relatively inexpensive DMX-controlled winches for lifting, like, you know, 1 to 10 to maybe up to 50 kilogram, I think, weights is like their biggest one, is their Wahlberg 50, their winch 50, whatever they call it. But it's really not a terribly complicated device. They're meant for, like, I need to lift a lantern, a chandelier, like drop a microphone to my lead performer or what have you. That's essentially what we're building. And I believe there is a, well, here, I think we did this recently, but let's review with ourselves. Let's find what is the control schema for these, and maybe we can rip it off if it's good, or we can at least learn from it if it's not. We'll pull up our manual for one of these Wahlberg winches and see how they did it. Because, like, and there's part of me that's like, we could do absolute positioning, you know, based on a DMX channel. But that doesn't really take into account, like, if we set a new, like, high or low limit, like, does that affect the positioning? So let's see, what did we learn? 7 channels of DMX control, the wanted position and speeds of movement. The movements are programmed as lighting. Yes, the winch 1 should be operated by an experienced operator and programmed according to the manual. Well, a bunch of modes: positioning with auto reset, positioning with manual reset, manual up, manual down, otherwise things stop. Okay, so DMX channels, position, so channel 1 is position rough and position fine. So a 16-bit control of position, max speed, max travel top, max travel bottom, find top position moving up, and presumably find bottom position moving down. So you mount the thing, you put a load on it. When the winch is ready, the first thing to do is reset it manually in mode 2 on DMX channel 6. DMX channel 6 is at 30%, the winch runs up. And so DMX channel 6 was our find top position moving up setting. The winch runs up, let it run until the snap hook at the end of the wire reaches the motor house. Decrease the speed as DMX channel 6 as the wire closes in the motor house. High speed could damage it. The winch is now reset, and the top position is at the motor house or where the motor was stopped. So you use the 6th DMX channel to sort of tell it where its high limit is. Positioning is set on the DMX channel 1 and 2. Where 100% is fastest and 0 is slowest speed according to DMX channel 3. Controlling the top and bottom positions. So positioning with auto resets. The winch resets automatically and also sets the top position automatically. I'm just trying to like parse what this winch does. The winch can be reset manually or automatically. The winch must be reset each time its power supply has been disconnected. Positioning with auto reset will always be at the motor house. Okay, so if you have this thing in mode 1 and it looks like there's an actual physical mode switch on it, it basically just runs up until the hook hits the housing, and that's top. And that's something that we could do. So I was looking at our little driver boards that we were playing with the other week, right? So these are the DRV 8825 stepper drivers, and they're on this little cheapy breakout board. Now, one thing about this breakout board, I'm pretty sure, is that it does not expose the fault pin as a pin we can actually, like, manipulate or, like, read from. I think that is true. Yeah, I don't see it. There's no connection point for it, at least. So we could maybe get at it if we were to take this board and use it separately, but I don't think it's something we have access to if we're going to make use of this breakout board as is. But one thing I was thinking about, especially like thinking about, you know, how do we like find a home position, is just to run it up until we hit an overcurrent limit, and then that must be our top position. Kind of, honestly, the same way that the Prusa Mini does its thing, right? Like on the newer Prusas, there are no physical limit switches. There are just dynamic stepper drivers, and so when it's doing its homing sequence, it just runs, you know, for example, the y-axis all the way until it hits what's currently on the left of the camera there, that big orange block that's holding the idler at the end of that arm, right? And so that when it hits that block, the current is going to spike, and the driver is just saying, oh, there's a current spike at this position, so we'll call that position 0, or at least the end on that end. And actually, it'll run to both ends of its travel to sort of measure the total distance in between and so on. But it's a switchless home sensing system. So if we had access to the fault pin on our driver, that's something that we could potentially do. It's a little bit scary just to be running things over current in the sort of limited capabilities that I have, but that's a possibility. But let's see what other options we've got. If we were to emulate the Wahlberg winch style of things. So we could do positioning with manual reset. The winch is manual reset on DMX channel 6. So this is like move the line manually, more or less, with channel 6 of the DMX control, and then when you stop moving it with channel 6, when channel 6 goes to 0, that's its top. Let's see, mode 7, manual run up. The winch runs up the speed set from the DMX selectors. This function can be used to test function or in association with on and off applying of wires, like you're spooling and unspooling off of your thing. So it's really like if home is not like at the body of the winch, then you have to like manually set it each time the winch power cycles. That's weird. I mean, I guess it's, you know, for an relatively inexpensive device, it is what it is. I just don't really love that idea. Although, we certainly could, like, make use of we could run this stepper slowly until it hits the top of its travel, and that's just home. And then we would define a maximum range of travel in our controller, or maybe with a separate DMX channel, and then that just becomes our range of travel. And we do have current limiting capability on these stepper drivers, right? That's something we did the very first time we were playing with them, is we adjusted the little potentiometer to be like, I don't want to put more than an amp into one of my little steppers, for example. And that should keep us pretty safe. The other way we could do this, right, as opposed to doing like a current limiting thing to detect when we are at the home of our step. Oh, hey, Thomas. Good to see you. Thomas, you missed a tremendous beer spill right at the top of the night. That was a lot of fun. But now we're into 2 successfully 3D printed things and thinking about how we're going to deal with limit switches, limits on the winch. Whether we want to do switches, whether we want to do something like the Prusa does, and like look for a current spike when the thing is hitting one of its ends. Let's think through the limit switch option, like because it's more complication, it's more work, but it is sort of the most I don't know, feels the most like tried and true, the most reliable to me. So in a lot of commercial winches, ooh, Hall effect sensors. Ooh, that's a fun idea. Yeah, we could certainly do something with that. Or the other thought I had was, so either I guess 3 thoughts. Hall effect is a good one. Physical micro switch limit switches, or like a beam break sensor, right? Where we have as soon as something is within, you know, we put a little stalk down, and whenever there's something within, you know, 12 millimeters of our shaft, that's our established limit. It would be nice. So what I was gonna say is, like, when I was working with hey Chris. Yeah, I thought that might pull some people out. Yeah, so we'll see about fire. More current is certainly a risk. What was I going to say? Something about limits. I'm sure I'll be totally candid. I mean, all you fine folks. I DM'd like a 4.5-hour session of the tabletop role-playing game that we're currently playing through with some friends, which was awesome. But I was like on for 4 hours, and I took a 2-hour break, and now we're back. And my brain is like hitting the little like speed bumps in thought. So as always, thank you for bearing with. So what I was saying, what a lot of like professional winches do, especially like some of the more like the fancier zero fleet winches, is they will have, you know, they will, like we are printing now, have a drum that spools the lifting line onto it, and that line will be going out. This is going to be sort of an illustration, right? If this represents a section of our drum, there is an idler pulley that directs the line out of the winch to wherever it's going to go. And as the motor spools that drum forward or backward, the idler pulley actually tracks along with it on a little ball screw, so that as the line gets wound onto the drum, it's being wound constantly in a nice, smooth, and consistent place, with more and more winding onto the drum. And then as it unwinds, the idler pulley spools the other direction, right? So you have this this nice smooth winding that's not sort of left to chance. We're going to leave it to chance, to be clear, but and in fact, what happens is, rather than in a zero fleet pulley, rather than having the idler pulley move along the drum, you have the drum move in relation to the idler pulley. So this is fixed in space, where the line is shooting off to, you know, lift your Peter Pan or whatever you're doing with it, and the drum, as it spins, is constantly moving up and down in just the right relation, so the point that the line exits the spooling drum is always in line with the idler pulley. And that just keeps things like nice and rigid from this point on. You're not dealing with the line fleeting off angle in addition to spooling and unspooling. So that's kind of classy. We're not going to be anywhere near that classy, but what I was going to say is, in a system like that, right, where your winding on your drum has a like, how do I put this? The positioning of your drum as it's tracking back and forth, as it's winding and unwinding, right? As it's spooling on, it's moving one way. As it's unspooling, it moves the other. You can use the travel of that drum to put a pair of limit switches on your frame. So you say, okay, well, if I'm unspooling to a point where my end stop hits this, then that's my high limit, and if it hits this other thing, then that's my low limit. And you can just have a pair of limits that are like just linear limit switches sitting on your frame, responding to the fact that you've set up your drum to move as it spools and unspools. So again, that's more complicated than I think we're going to get, but it's a clever idea. Thomas says, that's how my mover hums. Hall effect sensors not always the right solution, but they're always cool. Fact. When they are the right solution, they're awesome with basically no wear. Yeah, that is very true. So like, if we were to put, just looking to see which of my, sorry, you get a little tummy cam as I pull out my Boxo switches. Yes, trying to remember which box the micro switches were in. And they're in the box called micro switches. So yeah, so if we were to have you know, a little micro switch with roller, right? Obviously that's a mechanical component and is subject to sort of wear. And also, where would something like this go in our system? So if we imagine, right, that this is, let me get rid of the computer there. Imagine this is hanging hanging from our truss up here, and something's coming up to meet it from underneath. Maybe if we looked at it from the side with a little bit of truss, maybe that'll help it make a little more sense. Truss. So here's our block truss. Thank you, Cookie, as always, for the truss design. Oops, I hope... Oh, I see my headphones are wrapped around my microphone here. I'm going to... There we go. So if this was hanging off our truss like so, and so our batten or whatever it is being spooled up on our barrel, which is currently printing, and comes up to meet it or gets close to it, like where does this limit switch go that it's consistent across solutions? Like it probably has to mount like to one of these things, something like that, and then it gets tripped by something. But that kind of starts to limit like what we can actually lift with this setup, which is not super duper ideal. The thing about a Hall effect sensor, right, is we need a metal surface to detect, or at least a metal plate, which we could certainly do, right? If we had a bit of metal or plate or something, we mount the Hall effect sensor to, I imagine, one of these existing mounts, or maybe to our winch holder body somewhere, and the Hall effect sensor just sticks through there and measures when something's coming up to meet it. I kind of am just feeling like, there are issues with this, obviously, but something like a little micro switch that had a big plate on it somehow, that like could be mounted here with like a big wide, not even a plate, but like a big wide stick, so that like when anything comes up, whether it's a batten, a piece of truss, or something, comes up to meet this, it trips the limit switch, and that's your high limit. Oh, it's time to glue a tiny magnet on it somewhere. Yeah, that's not a bad idea either. Yeah, maybe we put, I'm trying to remember. Ooh, I have Hall effect sensors somewhere that I salvaged from something. That's what's going to make this problem. So, like, my sensors and, well, let's try the sensors and modules bin, because I think if I put them somewhere logical, they're in the sensors and modules bin. But I have this feeling that because I know they're salvage, that I have not sorted them into somewhere yet. I suspect, yeah, they had a big long tail on them when we cut them out of something. So I don't think they're going to be in here. Lots of other fun things. Well, I don't know if anything of this is going to be particularly relevant to our sensor issue currently. I've got a lot of this is left over from the electronics bash stuff. Like there's our wireless data sensors. There's some motor drivers, some L293s, a really early prototype servo mount. Wow, that brings me back. That's like a version 0.91 pan servo mount that's living in here for some reason. Here's another one. I think we were using these to like demonstrate servo motor control on Arduinos at one point. This would be an overkill solution. We could use one of these range sensors to try and detect when something's coming up to meet it. That'd be fun. Probably not super successful. I've got a little ham radio transceiver. I've got a relay module. It's fun to dig through your pile of stuff sometimes, right, and just see what you have. I've got passive IR, the most reliable sensor known to man, right? But no Hall effect sensors. So I think I'm not going to bore y'all with like tearing my workshop apart to try and find those tonight, but those might be a fun thing to play with. Yeah, I think that might be the way to go. So what we would do in that case, I guess with either kind of sensor, right, is we would, when the unit gets power, or maybe on like a reset command, it just moves up until it triggers that sensor, and that's its high position. And then we have to think about like maybe there is no down limit. I mean, this is so like I guess we could either pick that we define like how long the wire on the drum is. It just knows that, because that's the thing about those Wahlberg setups, right, is they have a fixed amount of cable on their drum, and so it knows that like full down is 30 meters or whatever they've been built from the factory with, whereas we might have a slightly more flexible system to play with. Now I wonder, let me pull out my box. Here's my box of winch parts. Here we go. You can see I've got a bunch of these like winch mount prototypes that I need to go back and salvage parts from. Like I could take the clip off of that and the bearing. Stepper motor drivers. Yeah, I'm not seeing the mount that I thought I might have, but that's all right. Well, never mind then. Let us punt on that and think a little bit about the next part of this project, which is, let's turn this back on. Okay. Which is going to be, so this mount we've solved, right? This is going to be held, this is our ratchet assembly, right? And this bearing we said is going to be held in place by one of our existing mounts here, right? The dimensioning should be exactly the same. So that's a piece of cake. The servo mount is still a work in progress. Ooh, I should print off one of these to play with tonight. That would be fun. I don't know why I haven't printed this part yet. That's our new handle wheel. Let's get that sliced, so as soon as this what we've been calling it, the drum is completed, we can get that rolling off. We'll still call this the handle wheel. So that's the part that translates the motion from the servo motor into the actual ratcheting force on the winch. So, handle, that's the same thing, right? And it probably doesn't want to print in that orientation. Probably wants to be like that. And this one, I guess I probably will do an adaptive slice on, just so those screw threads stand a chance of being decent. Let's slice that and see how it turns out. This at a pretty low quality. Another 38-minute print, we can do that, I think. So let's call this will be our handle wheel. And we've got not too long left on that drum before we test it. So we have a little bit of time here just to play a little bit with thinking about this servo mount. So one thing that I was thinking about is, so I have this form factor of servos, right? These little like NEMA 17 pancake servos. Steppers. I told you, speed bumps in the brain. But I also have an additional form factor of motors here. Now, where, of course, did I put them? Did I put them in the hobby servos bin? Yeah, I did. Apparently, I've been thinking stepper motors or servos literally all week. So I have this other form factor of steppers. You can see they have the same pinout, so I think they will be compatible, and if they're not, we'll learn something. They have a similar shaft, right, so they should be intercompatible. But I was trying to think, like, as I was thinking about the mounting for the stepper motors, is there any way to come up with a more or less universal mount that will allow me to experiment with different sizes of stepper motor that would still line up with this shaft? Assuming they all had the same output shaft shape, right? Like, if the hole in here is differently shaped from one stepper to the next, then like we're kind of out of luck. But I was trying to like think about how to be clever about this mount that would allow us to do this in a more or less sensible way. And thinking about like self-centering mechanisms in this way, like the thing that comes to mind is like a chuck, essentially. And this is way overcomplicating things, I'm sure. But like basically the impulse that I had was to build like a 4-jaw chuck that would grab the stepper in question, or maybe like a 3-jaw chuck that would do 2 opposite sides in the bottom. And allow us to sort of interchange steppers to play with different dimensions of things. Now that is even as I say it out loud again, like that is a silly, complicated thing to do just to hold a stepper motor. So maybe there is a smarter way to do like a thing that's meant to hold objects of different sizes. I mean, maybe it's something as simple as like we build the holder for this, and to get it to fit this, there's a spacer that adapts between the two different sizes. Maybe it's a holder for something slightly larger than this, and there's a spacer for whatever stepper you use. That makes some sense to me, and will also be a relatively easy part. All right, so that's 41.9 by 42.2. So let's do a quick and dirty mount for that. I think that'll be a nice project. And I think this stepper actually does not correspond exactly in dimension. This is just the part we pulled off of the McMaster car. Oh, that's pretty close. And that's pretty close. Okay, so this is not identical, but is close enough. So I'm not going to delete it, but I'm also not going to base any dimension sizes. Chris says NEMA is specific mounting sizes. That's fair. I wonder. So we could design a mount maybe that interfaces with these maybe front mounting holes. Is that what the Chris, you I think know more about stepper motors than I do. Is that what the NEMA sizes specify? I actually don't know. This was sold to me as a NEMA stepper, but I guess I don't know for a fact that it is. It's just from Amazon. But Chris, that's fair. NEMA 17 motor. 17 by 42 by 42. What are the mounting hole? Motor mounting hole. Aha! Okay. Give me a nice dimensional drawing here. Here we go. On the RepRap wiki. Amazing. Looks like, yeah, okay. So we can work with that. So they are 42.3 max and then 31 millimeters plus or minus 0.1 top to bottom, 31 millimeters plus or minus 0.1 top to bottom. Okay, Chris, that's a great idea. That's a great idea. We'll build a mount that adapts to that. And that actually might be what this is based off of. How about, let's see, how am I going to measure that though? Let's turn some things off here. Turn the frame off. Let's measure from that to that. Let's turn some more things off. We can turn the barrel, the ratchet, really everything except that stepper. Let's turn this off and we will turn, oops, get out of here. Barrel, ratchet, frame, handle wheel, pin squeeze clamp. Let's inspect these two. Do we have dimensioning on those? So the size of those is an M3 screw, so we add 3 millimeters out, so that's 31 millimeters or so. Yeah, so this really is a NEMA 17 motor. It's just slightly different exterior dimensions than mine. So maybe it's even a mount that incorporates this, well, maybe we leave this mount separate from the motor mount. I think that's probably for the best. But we could make use of that bearing mount we have already designed as the basis for this motor mount. That would probably save ourselves some labor here, huh? Because we know that this hole that we painstakingly developed the other day is the right distance on center from the hanging point of the clamps that are attached to it, right? So that's a useful thing not to have to reinvent the wheel for. So let's call this our NEMA 17 support. And let's think about the least awful way to do this. Oh yeah, I got lazy right here, right? This is the one where I didn't put this body in a component when I started, which I should have. So we may have to work backward a little bit here. So here is our sketch that's defining that hole. And that hole is actually, so like what is the height of this mount here is 22 millimeters. So let's make this interior hole at least 22 millimeters. It's just over 22 millimeters now. It's 22.2 millimeters. That's hilarious. Let's make it 25. All right, and that's the hole through which our motor assembly will protrude. That's according to the dimensional drawings, which Chris and Thomas very helpfully pointed me to. Thank you. That's this plate is 22 millimeters across, this bearing surface here. So we'll make our hole slightly wider than that so that our motor can stick through it. And then we just need to add our mounting, our holes essentially on the back, or wherever we think of these holes being. And those are on 31 millimeter centers. So do we need to extend this body so that it comes down lower? That's 37 millimeters, so probably, yeah. Let's see, this circle to, oops, you're not even looking at that. You're looking at this. Let's see. Yeah, I think we need to see where's our shape where we're defining the bottom of this. Is it this? No. Where are we defining the overall height of this shape? That's where we're defining the hole that we're punching in it. That extrudes. That is our cut. Let's see. Let's roll. Let's use our history marker to explore this timeline a little bit. So it's at this point that we get everything joined together. And here's our reference plane to come all the way down here. So rather than extruding to that plane, let's extrude to a plane which is somewhat lower than that. Yeah, so let's come like 7 millimeters further down from that, and we will redefine sketch plane on this sketch that like sort of defines the bottom of our piece. And now that extrusion, yeah, so that all just gets bigger. So there's our new shape. And now let's put some holes in it. I'll put a sketch on this plane. We will draw out a rectangle here, which is 31 millimeters divided by 2 along each side. 31 divided by 2. And that's where our first hole is going to be. And then we'll just mirror that out to get our 4 different mounting holes. Let's see. Pretty sure NEMA doesn't set a hard limit on the actual sizing of the NEMAs. It's good to know, Thomas. Like I say, I'm not super duper familiar with these things. It's just part of why I'm doing this project, right? Like I get to learn these things along the way, and why I'm always grateful for y'all being here, because, well, y'all usually know more than I do, which is great. So there are our 4 points, and then we'll just use our built-in hole tool. We probably don't want to thread these. That seems a little bit silly. We'll just make them a clearance hole. So we will make this a single hole flat drill all the way through, and we will make it like a 3.6 millimeter hole, which is pretty good for clearance for an M3 screw, if memory serves. So there's basically our mounting plate. I do wonder if this wants to be a little bit skinnier. Just to accommodate, but I'm not sure if doing that's going to break everything. Let's see. Oops, not 60. Jesus. How about 6 millimeters? We'll see if that breaks everything. Please don't break everything. Oh, well, it kind of broke everything. Oh, but maybe we can unbreak it. Here, hang on. It looks like this top section is now just skinnier by a 0.5 millimeter than the bottom section. Yeah, because we need to change that sketch later on where we define what the bottom of our shape looks like. Yes, there we go. So we can now, oh, and we did, see, I didn't do this in like parameters or anything. Oh, and you know why? It's because we made that plate 7 millimeters because that's how wide the 608 bearings are, but we don't have to dimension off that anymore because there's not going to be a 608 bearing in this piece. 6 millimeters. And that's pretty good. And now we need to make this part smaller. There's our bottom, so we will just reproject our body back in and finish sketch. Extrude to object. How did we do this? All right, let's go back to roll history marker here. So this is what we had, and we made this sketch, and then we did in a single extrude, we like somehow did that. How did we do that? Oh, because this is a join? To object. I've clearly confused it. Well, really, I'm going to undo a bunch of these steps. Sorry for the waving all around. As long as these shafts are at least 7 millimeters, we should be okay. And this one appears to be 12 millimeters, and this one is going to be at least that. So we'll be all right. 20 millimeters, yeah. So that'll be fine. We'll leave that as a 7 millimeter mount, which may be good because this is what the motor's going to be hanging off the back of, really. And maybe, well, we'll print one of these and we'll see how it goes, and then we'll think about whether we need to like stiffen it up with some additional support or something. So let's bring this into our other drawing. And here we go, NEMA 17 support. And we will do a point-to-point move of, here's this circle gone. Let's see, I want to move this component, do a origin point of this circle wants to be matched up with this circle. Yeah, there we go. That's what we're talking about. Here, we'll just chooch it out a little bit for clearance, just because we can. Boop. All right, so that's where that mount is going to go. So let's turn that frame and barrel back on. We'll really start to get a sense of it. Yeah, so the motor will be, I guess this will be flush up against that motor, because that's what the motor is mounted to. So let's move this nice and flush. Let's see, create selection set, view in window. Now I want to move copy this whole component here closer to that guy. And this is just an approximation, of course, because like this isn't the actual stepper motor, but it's just as long as we're thinking about how the system assembles, that's what it would look like. Is something like that. And that'll be nice too, because that allows us to pretty dynamically position the stepper in relation to this handle wheel and to the rest of the assembly, which will be nice, because I'm not sure how deep that's going to want to be. And we are going to need a little bit of like forward and back travel in that stepper. Oh, you're still looking at the table. Jiminy crickets. Jiminy Christ. Ooh. But speaking of the table, that barrel came out all right. Looks like I forgot to remove all of the spacers from the slicer before I added this one. So this one's a barrel with a little friend. Jeez, it's a good thing I'm not like doing heart surgery tonight. It's a good thing I'm not doing heart surgery any night, frankly, but tonight in particular is a little bit rough. So this is a little bit more spoilage on the overhang here than I had been hoping for. So maybe we will print this with some actual supports, or maybe we'll just like loosen the overhang, like reduce the overhang angle a little bit. But as a proof of concept, that's not bad. So that as a winding barrel, right, will go onto the shaft like so. Onto the shaft like so. It's getting like stuck partway through, which is weird because the diameter of that shouldn't change, but it certainly feels like it does. What are we getting? Just like maybe there's some artifacting due to the hole that we're getting hung up on, or due to that like hole in the side that we were going to put the grub screw through. But yeah, it goes in super easy from this side, and then it gets to a point. I mean, I can see the shaft through that hole, but I can't go. Well, you know what it's time for? Everybody's favorite. Other than my wife and fire, I guess. The third favorite thing on the stream is filing. Let's try that again. No, it's like really stuck in there. Huh. I do wonder if it's to do with like, you know, and it was printing some part of the overhang or something due to that hole, that something is blocking our path. Yeah, we're gonna get there. I just want to see this thing on. I mean, this derpy little like drum with this spacer welded to it. Oh gosh, Thomas, we're gonna make it work or die filing. You're killing me here. let's see. Let's try. So it's interesting, like if I go in from the other end, it's still like the whole thing is super tight up here. Did I goof? Did I goof? Did I goof this design up real bad? No, that interior surface is like all one thickness. But clearly it's the way it's printed is that it's much tighter on this this upper section. I guess this is the lower section, given that this printed closer to the print bed. That's so bizarre. It's super, super tight. Well, more filing. Everybody's favorite. There we go. There we go. Get in there. No, that's so strange. I'm gonna like rip this drum in half trying to get it onto the thing. But see, from the other angle, it just slips right on. I'm baffled as to like what's actually happened in the printing process here to make this the case. We're getting closer though. We can see that shaft coming right up at the end. Probably with too close to the camera to focus. You can see him like within an eighth of an inch of being free. Let's get this thing on here. Now I think what's happening is I by shoving it in and out so many times, I've created a little burr. That's like I'm catching on every time I put the shaft through. So I'm actually hurting myself as I... There we go. Yay, we did it. Get that tape out of there. We'll put our shaft support back on. That might need retaining rings. I can see that slipping out already. But now, again, we would put a grub screw in there. But now as the shaft rotates, put it on the table so it doesn't spin the whole assembly. Right now, we have our barrel that could wind and unwind. You can see that spoilage there. Gosh, that's nasty. It would wind and unwind our lifting lines. That'd be kind of fun. Yes. Now where were we? Oh, right. We were gonna print a crank handle, or a handle wheel. We've been calling this, which seems like a good thing to get done. But yeah, I gotta think more about hardware for these limit switches. These are the limit setting devices. I'll be honest with y'all. I mean, I know all of y'all pretty well after a year or so. Both Chris, Thomas, whoever else is hanging out there and watching after in YouTube land. That's 2 wins and a loss. I think for tonight. It's just where I'm gonna call it. I'm beat. I'm screened out for the day. We got some good prints. We got the spacers working. We got the barrel working. We had some good thoughts about NEMA 17 mounts. We had some good thoughts about how the barrel's actually gonna mount. And I'm just like struggling to pull the brain power together to keep it going. So I'd rather call it and come back fresh in a week and put some things up on Twitter and like actually work on this when I have brain power rather than just like force it through, because y'all get it. Y'all have been there. So yeah, sorry for the abbreviated stream tonight, but just life has been real busy. We opened the plane exhibit, the 727 at the museum this week, which was awesome, but kind of a slog. Not a slog, just like a marathon. We're kind of to the end of a marathon, and it's done, and it's open, and it's great. And now we're also the team that cleans up after the marathon, so there's still some work to be done. So yeah, that's actually where I'm going to call it tonight. Thanks so much for watching. Find me on Twitter, ask questions. I hope you're all doing well. We'll hopefully be back here next Sunday night at 7 p.m. Central. Find me on Twitter in the meantime, details at jeff.glass/Demilight. And yeah, we'll just call it there. Thanks, y'all. I'll see you next week.